Today I shall take time to explain the dispersed systems formalism, DSF. It is a formal system that allows describing food in particular, but not only. It could be applied to cosmetics, drugs, and so on. It can describe, but it can also produce new ideas. So it is both important for research, scientific research, and for innovation. Let's start from this question. What is food? Here, in this picture, we have a dish, and a dish is clearly what the English people name food. Okay. This dish has been produced by a chef, I mean a three-star chef, and there are various parts. This is quite obvious. So indeed, this organization is at macroscopic level. We just see with our eyes. Now, if we look more in detail using a microscope, at any part of the dish, we will find a different organization, which is a microscopic organization. So let's come back to the main idea. The macroscopic organization reveals some parts, and all these parts have each of them a microscopic organization. And now, if we look at the various parts in this microscopic organization with a stronger microscope, let's say a nanoscope, then we will see a nanoscopic organization. For example, in this picture, you see the casein micelles of milk. Indeed, casein micelles is not the right term because it's not only caseins, which are proteins, but also calcium and phosphate. Anyway, these are objects at nano scale, and of course, if you go deeper, you see a molecular organization. In this picture, of course, you don't see the molecules. You see raspberries. On the left, you have the raspberries out of the bag. Now, on the right, I've added some tin 2+ ions, and immediately they stack with some molecules from the fruits. Of course, these molecules are anthocyanins, but it's a detail. What we want to see here is that there is a molecular, it is the result of the molecular organization. So now, of course, this slide is in French, but it's not so important because on a slide you don't display text that you read. So I can just translate what is in red. Notation can lead to discovery. This is the first important idea from this treatise of logic by Goblet. And the second part says, if you have symbols, and if you combine symbols, you can make formulas, and then it is very fast and efficient. So, indeed, Lavoisier, the chemist, Antoine Laurent de Lavoisier, the father of modern chemistry, published a text in which he introduced the chemical formula. And this is the paragraph in which he says that in order to help to understand the state of a question, and in order to present immediately the result of what occurs during metal dissolution, he says, I built some formula that look like algebra, but are not from the same kind. We are far away having in chemistry the same precision as in mathematics, and these formula are annotations to make the thinking easier. It's very important, and I copied Lavoisier, not for chemistry, but for describing the organization of physical systems at any scale. It is quite simple because you have operators, you have 5 of them. So slash means randomly dispersed. We will see some example later. Plus, when you have 2 faces, arrobas for an inclusion, sigma for a superposition, and x for intermixing of 2 faces. Now, you have the faces, bottom right, gas, solutions, oil, and solid. And you have the dimensions. The dimensions are mathematical dimensions. So dots, lines, sheet, and blocks. We are going to see that in more detail now. So for example, for chocolate, this is a microscopic picture of the surface of chocolate at 20 Celsius degree. The temperature is very important, of course, because everybody knows that when you cool the chocolate, it is very solid, but if you eat the chocolate, it melts. So at room temperature, you have part of the fat of cacao butter is solid and part is liquid. Here you see only the solid part. The liquid is inside, which means that really this is a gel, because a gel means a solid with a liquid inside. Okay? So, of course, it's not only fat in chocolate. You have sugar crystals, plant material, and so on. But anyway, you see we have solids and a liquid. Now, this is what people call the cream of an espresso coffee. It's just a foam. What you see here are air bubbles, and air bubbles dispersed in a liquid makes a foam. Now, this is the definition of a foam by UPAC, International Union of Pure and Applied Chemistry. You find that online. You have the Gold Book, very, very useful. And using this definition, it's clear what you say. So I invite you to always use the UPAC definition. So for a foam, here you have the definition. Small structures of gas dispersed into a liquid or a solid, depending on which foam it is, either a liquid foam or a solid foam. Now, here it is a microscopic view of shallots. So you see the plant tissue is made of cells that are adjacent, and they are, let's say, glued together with the cell wall, and the cells are full of water. So indeed, a plant tissue is a gel, and the gel are defined, of course, by UPAC. This is now the definition by UPAC. You see, a gel is a non-fluid colloidal network that is expanded throughout its whole volume by a fluid. Okay, so of course the definition is longer because there are different kinds of gels. But anyway, the former one was a gel, and this one as well, even if it is more complex, because you see, it's a potato. The color has been simply added by putting some iodine on a very thin slice of potato under the microscope, a very simple microscope, and what you see in dark blue are the starch granules. So you can see, let's say, 10 of them in one cell, and indeed you have the solids dispersed into the liquid, and this liquid is dispersed into the big solid of the potato. So you see, it's more complex than a simple gel. When you look using the microscope at egg yolks, you see granules dispersed in a plasma. A plasma is let's say, a concentration solution of proteins, but it's a solution anyway, a liquid. And you have granules, and these granules are considered as solid because they don't flow in a way. They don't flow. One granule does not flow. It's behaved like a solid, a soft solid, of course, but it's a solid. Now, imagine that you want to make a custard and you would add some sugar. What you see are the sugar crystals dispersed into the former system. So, indeed, when you look now at this picture, you see the solids dispersed into what we could consider as a liquid, because the liquid is a continuous phase. When you whip the egg yolk plus sugar, it becomes more white. And why? The microscopic picture tells you that you see a lot of air bubbles dispersed into the liquid. And slowly, the sugar crystals dissolve. So you see, when you whip an egg white with sugar, you make a foam. And it becomes white, just as egg white becomes a white foam. Now, when you cook this preparation in order to make the custard, under the microscope, you see clearly that there is a coagulation. So now you make solids dispersed into liquid. The name is suspension. You make a suspension. This is the same story for béarnaise sauce or hollandaise sauce and many other sauces. Now, I want to come back to gel. We have seen one gel, plant tissue. Now, here is another gel, meat. Meat is made of long fibers full of liquid. So, indeed, it's a gel. Using gelatin, you can also make a gel, but it is a very different gel because now the water is not trapped into bags. A compound dissolved in water could diffuse from top to bottom or left to right. So it's a gel, but it's a different one. And also the cooked egg is a gel, either for the egg white or the egg yolk. So I told you that in gelatin gel you can have some diffusion, and for other system you don't have it. So you can make a category. So it could be connected gel and non-connected gel. So this one is gelatin, two concentration in gelatin, 5% and 20% with water. So I made two gels, and I put a drop of methylene blue at the top of these two gels, and you see the diffusion is different depending on the concentration in gelatin. So now, of course, we see a difference. On the left, you can have a diffusion. On the right, you can't. But how many gels are there? In the past, it was thought that you had probably 8 kinds of dispersed system. For example, when you disperse a gas into a liquid, you make a foam. Or when you disperse a gas into a solid, you make a solid foam. When you have a liquid into a gas, you have a liquid aerosol. But when you have a liquid into a liquid, if it is not, if they are not mixing, you have an emulsion. A liquid into a solid makes a gel, as we have seen. A solid into a gas, a solid aerosol. A solid into a liquid, we have seen that already. It's a suspension. And finally, a solid into a solid makes a solid suspension. But what is this system? Indeed, we have seen that it is probably a gel in a way, but it's also a suspension. So is it a gel of suspension? It would be quite long, and we need to find an easier system for describing the potato. So let's come back to this DSF, and let's apply it to various cases now. We need first a scale, and the scale will be the scale that you use for looking at the particular system. For example, here the scale would be microscopic. Okay. We have to get a very clear idea in order to make the analysis, and I call this idea the idea of orders of magnitude. So imagine that you have a spectrum. Here it is a nuclear magnetic resonance spectrum. If you are far away, you see only one signal. It is very simple. So indeed, because it is 4.7, it is water. Okay. Now, if you multiply by 10, I mean, if you amplify the signal, you see more, and now you can analyze the, let's say, 4 signals that you can see, because you don't need to take care of the big water signal. It has been done already. When this has been done, you can multiply again, and this is the idea of multiplying. So now you, after some time, you reach the noise, and when you have chosen one scale, now you can make a formula. For example, for the sauce mayonnaise that you make by whisking oil into a mixture of egg yolk and vinegar, you disperse oil into water, O/W. Of course, you can add more quantitative information, but let's focus on this simple O/W. You disperse oil into water, and the dispersion is at random. Of course, in this picture, you can see 3 black circles. They are air bubbles. All the other shapes are oil droplets. Okay, but you could say, okay, but if we have air bubbles, it can be a foam. No, let's be simple. The main system is an emulsion, and indeed the 3 air bubbles are artifacts. So, of course, I said emulsion. You need the definition, and you find it in your pack. So, a fluid colloidal system in which droplets are dispersed in a liquid. Okay, there is more about that, but let's keep that for the moment. And let's come back to the potato. And now it is very easy to describe what you see. You see the starch granules, S1, randomly dispersed into the water inside cells, so S1/W, and all this is dispersed into the potato, so /S2, and S2 would represent the whole potato. You can add more information about quantities, scale limits, kinetic information, and so on. For example, describing the making of mayonnaise, you could use either the first equation, that looks like a chemical formulation, or the second one with a parameter, a time parameter, for example, or the third one. I don't go into details, just to say that, of course, you can always increase the formalism to make it fit better with reality, but you need to keep in mind that it will never reality. So you have to choose exactly what you want to describe, and the choice is made from your goal. Now, dimensions. Okay, I told you that dimension 0 is for dots, dimension 1 is for line, dimension 2 is for surfaces, and dimension 3 is for blocks. Okay, of course the line can be folded, for example. So, and it is only the mathematical dimension. There is a very clean definition about that, but let's keep the intuitive idea. And now you can mix the dimension of the faces. So on the left, you have the formula for an artificial meat. A meat is fibers, including a liquid. And the liquid is more or less jellified. This is exactly what we did. In the middle, it is an artificial orange. So you see the formula is more complex, but in this formula we described as well the liquid inside of the, let's say, pearls, but also their skin and their distribution. And on the right, it is the choucroute. The choucroute are filaments dispersed, making a block, okay, solid. So now we come back to the former picture. Here is the formula. You have a solid 1, which is the white upper ball, over the solid 2, which is the yellow one, over the liquid. Now, for an emulsion, you have oil droplets. They are dimension 0, and they are randomly dispersed into something of dimension 3, and this something is the liquid. Now, for the casein micelles or for the complexation of anthocyanins with metals, you see, here is another formula for gels. D0 water, because you have the inside of cells, randomly dispersed into the solid, which is D3. Okay? And using the same formula, you can make an artificial orange. So you see, you can use the DSF in order to make a description or to make something new. Now, for some gels, of course, we said that it was more complex. Here is the formula for the potato, for the meat, for the chocolate. I told you that sometimes there can be some diffusion. There can be more complex gel. And, of course, we can come back to this picture of the fibre, artificial meat. And now we can distinguish among gels. So you see, there are two gels, gelatin on the left, shallots on the right, plant tissue, and they don't have the same formula. And this is very important because this system don't behave the same. So if you want to study their behavior, you need to have a clear description. Of course, the number of possibilities using the DSF is infinite. And in this picture, I made something funny. I took my computer with the random function, and I asked the computer to create a formula at random using the right rules. And this is the formula at the bottom. And over it, I represented the real physical system that you could make after this formula. Okay. And indeed, some years ago, many years ago, I decided to create a dish in honor of Michael Faraday. Michael Faraday on the right is probably the best experimentalist of all times for science. He was a wonderful man living in the 19th century in England. He discovered benzene, he discovered electromagnetic induction, he discovered the Faraday effect for optics, and so on and so on. He was a wonderful man. So I decided to create a dish that would be called a Faraday. So I chose a formula, and I proposed a recipe for a Faraday of lobster. Now, how is this formalism useful? A long time ago, I decided to take all French classical sauces, here there are 451, and I used a microscope in order to understand their physical nature and to create some laws. So, of course, we know some simple sauces, emulsions, solutions, foams, gels, and so on, but how many? So here is a table that I produced. So you see the name of the sauce, now the recipe. If the recipe is derived from another one, I make a new column. Now the formula. The formula can be complex, so I can produce a reduced formula, and so on. And finally, I discovered 23 categories, only 23. So here is a list of the categories, but what is interesting, they are ranked by complexity. But some easy sources are missing. So it's funny because using the description given by the DSF, you can make some order, but also you can detect some systems that were not produced in the past, and you can make them. So you see again a description and innovation. Why only 23 categories? This is the number of categories of sauces, of French sauces in the history. It is after, let's say, the beginning of cookery books. So you see on the right the number is increasing. On the left I put the Apicius Deire Coquinaria, which is a very old book. It is in Latin, not in French. But you see the number of sauces has increased for French sauces. And of course now it's finished because you can make an infinite number of formula and you can make new sauces. The big question that I would ask is this one. You have a set of all formulas. You can make them into physical systems, and these physical systems have chemical and physical properties. For example, flavor release or optical properties and so on. Can we predict the properties from the formula? This is a very interesting question. Similar to the one that you have for drugs, is there a relationship between the chemical formula and the biological effects? So indeed, now moving to making new systems, the orange system at the middle of this picture is a big pump, and this pump was pumping water, oil, and air into the small system on top of the blue part at the bottom. So now I explain, I used a simple formula and the pump, and they were microreactors. On the left you have microreactors. And this is the first dish in the history of cooking that was produced after a formula by a machine. So very simple. Now we used computers in order to drive the pump. So you type the formula, you get the result, and you made some cocktails in a public fair. There is a very small system now, prototype. I call it a pianoctel. And with this system, this is a microfluidic system, you can make 500 billion different systems. So you see, using the formula is very helpful. In order to calculate how many gels you can make, it's very simple. You make a computer software, and you find all the gels. So you see, many of them are completely unknown. So these gels have been really discovered. Now the question is to look for them in nature, but perhaps some of them don't exist, so we can produce them as well. Here they are, and finally here they are. For suspension, the same kind of story. Suspension, you remember, they are solids dispersed into liquid. You make a small program, and you calculate the simple suspension. Here they are. Now, you can make more complex suspension with two phases dispersed into the liquid, so the same kind of software. And now, the result, I'm giving only the beginning of the result because there are 362 systems. Why only 362? I don't know. This is the beginning of a story. We are in the middle of the work, but of course, with the same kind of software, we can make more complex gels or suspension in foam, suspension in emulsion, suspension in gel, and so on, and so on. Very simple. For all these systems, we have a special bioactivity. Bioactivity means, let's say, the release of a biological compound from the system. Sometimes the release is very fast, so this is the curve on the left. And sometimes it is slow, but it increases later and it lasts longer. Can we make, for example, a food with one flavor that would appear, disappear, another one would appear, disappear, another one would be, and so on? And the answer is yes. We did it in, it was in a culinary shop near Aarhus in Denmark, and with Danish chef and and PhD scientists, we produce this kind of food. All this is described in the Handbook of Molecular Gastronomy, and now I give you my email if you have questions.